we're completely shifting gears now. We are starting matrices. This should be, you'll see the quiz. My expectation is that you can do everything on the quiz. Try and do all the quiz questions by hand, just for practice. It's all 2x2 matrices. If you want to use Mathematica to check, go ahead and do that, but just make sure you can do it by hand. We are starting matrices. We're going to use them because they're going to be the #1 tool we use when we do linear vector spaces. So I really want to make sure we're all on the same page. I'm going to be going through a lot of stuff pretty quickly on the assumption you've all done a lot with matrices already. Most of the issues will be Mathematica issues. But I do want to cover everything quickly. And so if you see things that don't make sense as I go through them, again, come to office hours, or make sure on Thursday when we do the group questions you're really getting everything completely correct. I don't know why I find the most confusing thing about matrices is trying to remember which index is the row and which is the column. This is one place we have a very strong convention. The first index is the row, and the second index is the column. And when I write this notation, A sub ij, this is a very particular type of thing we're doing. This will often, sometimes it'll be called components, but that's usually more reserved for vectors. Sometimes it'll be called index notation. Often it'll be referred to as the matrix elements. And it's a common convenient notation to use when you are worried about doing the elements. It comes in real handy when we're doing lots of stuff. Unlike vectors, which are either almost always an arrow on top or bold if you're typefacing, or italics, and I will usually use arrows because I can't do bold and italics when I handwrite. Matrices don't really have a standard notation for indicating them, so you kind of need to know that it's a matrix. And it's usually obvious from the situation. In Mathematica, and I'm not really sure why, but I think it's to distinguish between functions and matrices. Mathematica uses a double square bracket to index a matrix. In Mathematica, in its core form, matrices are just a subset of lists which can be any dimension. And they're indicated with a set of brackets. Actually, let's do it in the notation we have above. And the way the brackets work, I found it took me a while to get used to it. I think for some people it's more logical. But each of these is a row. And this will be the first index here, basically goes one bracket in. That's the first index. The second index goes inside those first set of brackets. So this is our j going from 1 to 2. This is our I, 1, 2. And what's nice is it makes it fairly easy, if you get this process down, to go to any dimensional. Right, so if I do I, j, k, I'm going to have 3 sets of brackets. So I might have an element 1, 2, an element 2, 1 inside this bracket. At this level, maybe I'll have 3 of these objects. So I have 2, 0, 1, 3, and I have 0, 1, minus 1, 2. And then I have my final bracket. So if I look at it, these are my most these are my kind of level 2 pieces. These are my J's. And these outer ones right here, those are my I's. And then all the little numbers inside are my K's. So I work down, as I go across I, J, K, I work down inside my brackets. And you want to be able to parse those chunks. And I'll show you there's nice ways of presenting these using matrix form and other things. It's harder, once you get 3 indices, it's harder to present it nicely, but there's ways to do it.
What would that look like in like a matrix?
See, this is not a matrix as you would like it because it has 3 indices. So this is a higher thing. In math, we would often be, this would be something we might call a third-rank tensor. If it had the right properties of a tensor, meaning it has 3 indices. So it's something when you have to keep track of 3 directions or 3 indices. You want to loop over 3 things for some reason. We don't see these a whole lot in physics. There's a particular one we use a lot called epsilon ijk, which you may have run into, but probably not yet. So in physics, to go down to 3 indices, not going to happen a lot. In abstract math, a lot. 3, 4, 5, 6, 7. We can do n of these. So Mathematica, I'm just showing you ahead of time, has this built in as a functionality if you wanted such a structure. This is going to look like a normal n by m matrix. And if you have 1 index, it'll look like a vector. And we'll do some more of those. Now, addition of matrices is pretty straightforward. We add the individual elements, subtraction, subtract them. We don't really do division of matrices. If a matrix happens to have its inverse, we can multiply by the inverse. That's like division. Multiplication, hopefully you're all familiar with it, but I like to just kind of show it with an example, right? So we take the row and multiply that by the column, element by element, and sum. So we do 2 times 1, which is 2, plus 3 times 2, which is 6, and we get 8. And then for the next element here, we take the second row times the first column, and that's going to go here. Anyone tell me what that is? 9. What's going to go up here? And you have no idea where I'm pointing. What's going in the upper right? 3. And the lower right? 4. Okay? Now, in Mathematica, you have to use the dot to get this type of multiplication. And I'll show that to you when we switch over to the Mathematica file. Now, how do we write this? If this is A, this is B, and we want to get C, we're doing A times B equals C. And this is where index notation or elements comes in very handy. What we really want to know is, what does CIK equal? What is this element of C? And this would be the IK element of multiplying A and B. That's the easy step. And what we noticed is we did a sum over J, where J was the columns of A and the rows of B. So what do we do to get an element? We pick a row of A. That's what we did up there, the top row, 2 and 3. We picked a column of B. That was K. So to get 1, 1, we picked the first row, first column. And then we summed. What did we sum over? We summed over columns in A, rows in B. This points to a very handy mathematical notation that is useful in a ton of physics. How many of you have used repeated index notation?
Is there another name for that?
Sometimes it's called Einstein notation.
Yeah, I saw it last.
Yeah. So what it is I say A times B, the ith k element of that, which is CIK, I just write it as AIJ BJK. This is what we call a repeated index. It's repeated within the same term. This is something that's key. If I write A plus B, the ith j element of that, that's aij plus bij. These are not repeated indexes because they're in different terms. So there's no implied sum. This is repeated in the same multiplicative term. It tells me I sum over these. And it saves me writing. But it actually turns out to be a very efficient, better notation. And once you get used to it, it really allows you to keep track of sums much better than you would otherwise. And for instance, where it becomes powerful is recognizing, now what if I want to do a matrix times a vector? Well, a matrix times a vector equals what? Another vector. So how many indices am I going to have at the end? 1 for the vector. So I'll find the ith element of this vector, and I'll do it by taking the ith row of my matrix. The ith row of my matrix, the j columns summed over the j elements of V. And notice one of the things that happens when I have a repeated index, that index goes away. My answer only has the same number of indices as I hope it has. So I should have one index left, so I should have one unrepeated index in my expression. So it allows you to check if your expression's correct. And so this has an implied sum.
Are you supposed to do that for every index in the vector to get like complete?
So to get the whole vector, I would do it for, say, if it was a three-dimensional vector, I would do it 3 times for I equals 1, 2, and 3. Because each of these is an element. And then once I'm done, I have all the elements. So this is a way of writing all the elements at once in sort of an abstract notation type way. It should also then immediately show you that if I wanted to do V times A, this must be something different, because this is Vj times Aji. Right. The ith component of this is a different beast. It's using the columns and summing over the rows. This is using the rows and summing over the columns. So they're just different things. It also means if your matrix is not square, one of these two may not work, or shouldn't work, because the vector is only going to, right, this only works, this one works when the number of elements in the vector match the number of rows. This one works when the number of elements in the vector matches the number of columns. If either of those are not true, you can't do it. Now, a few other notational things using index or element notation. If I want the transpose of the matrix, I just switch my indices, because transpose is switching the rows and the columns. The other big thing we have to do in physics is we have to take the Hermitian conjugate, or a dagger. So you have to be real careful of my writing. That's a dagger, that's a T. This is the Hermitian conjugate, or dagger. And that is just AJI, but the complex conjugate of every element. So it's the complex conjugate and the transpose together. The other thing we define, of course, is the inverse. The inverse is defined by A inverse equals 1. And we define an idea called the commutator. How many people have used the commutator before? Not many of you. Okay, so this may be the one new idea. This is A comma, b, and it's defined as a times b minus b times a. Why do you think we would define an idea like that for matrices? Why would we care about what a times b minus b times a is? If I told you I'm going to look at this for real numbers, would it ever be anything interesting? What would it always be? 0. So why do I define it for matrices? They don't always commute. That's the key. And this is absolutely central in quantum mechanics. Because what it says, if they don't commute, doing b first and then a is different than doing a first and then b. Because these two objects are different objects if they're not the same. And that's a central idea in quantum mechanics. It's exactly where the uncertainty principle comes from. This is the uncertainty principle in quantum mechanics. So it's an important idea, and you want to know if it does equal 0, then they commute. And that's really key. Finally, something we'll spend a lot of time on is the determinant, which I'm not going to define here, and the trace, which is the sum of diagonal elements. And the key way we can write that is a sub ii. Notice by writing it as a sub ii, I use my repeated index notation. This is not a single element. It's a sum of all the diagonal elements. It's a sum of all the elements where these two indices are equal. The key thing about both of these are scalars. And what we'll find when we think of matrices, which we'll do later as tensors, these are objects that live in coordinate systems. And what do you know about a scalar? If I change my coordinate system, what happens to the scalar value? So if I have a coordinate system, x, y here, and I tell you that my mass is 10 kilograms, and I rotate the coordinate system, does anything change to my mass? No. So what happens to scalars when I change a coordinate system? Nothing. So the matrices, the scalar properties of it, its trace and determinant, cannot depend on the coordinate system. The individual values I stick in do, right? If I have this coordinate system and I rotate it, what just happened to the components of the acceleration due to gravity? They changed, right? They're different now. And so vectors and tensors, which are represented by matrices, change their components under changing a coordinate system. Scalars do not. So these are two properties of a matrix that become very important because of that.